Section 1.3 introduces the concept of vectors, and then the first 3 pages here are sort of some definitions and sort of getting our feet wet with what vectors are and what they look like in different dimensions. And then the final couple pages are really how we start thinking about vectors in our application to linear algebra. And so we can think about a vector as being a matrix with just one column. And so, for example, if I write a matrix like this with just one column, 4, 5, 6, we would call that a vector. And since it's a column, we could also think about it as a column vector. And it could have any number of entries. And so here's just sort of a general example, x1, x2 through x6, that has 6 entries. Now, I just wanted to do a couple examples here because we define, as a quick reminder, we define matrices and vectors using the notation m by n. So this one right here is a 6 by 1 vector, and we think about the first number as the number of rows and the second number as the number of columns. And so this first example right here is a 6 by 1 column vector. Right, this one right here would be a 3 by 1 because it has 3 rows, 1 column. It's not too challenging to go from the idea of a column vector, which goes up and down, to a row vector, which goes side to side. So you can think about a column vector as like a column from a matrix, and a row vector would be like a row from a matrix. So a row vector might look like this. Now, if it's a row vector, it goes 1 by something, right? Because there's 1 row and 3 columns. And we can have any sort of different number row vectors as well. G, H, I, J, K would be a 1 by 5 row vector. If we just have a constant number, so just like the number 2, or the number pi, or the number e, or the number 1/2, any sort of just number that's not in a matrix is called a scalar. And we'll see why in a second, because those things are used to scale vectors, right? That's a very common math phrase. Scalar, you just think of as a constant. Now, when we're looking in a textbook, or in my notes, for example, the book often uses bold to show that it's a vector. But if we're going to draw something by hand, we can't make something bold by hand very easy, and so instead we put like a little vector sign over something to indicate that it's a vector, right? So if I write something like x with the vector sign, we know that that is some kind of vector. Okay? But if I just write, for example, x, that's going to be a scalar because it doesn't have a hat, and so we're thinking about that as a constant in that case. All right, so just some notation, a few definitions to get us started. Adding vectors is really, really easy. The key thing here is, though, when we want to add 2 vectors, they need to be the same size, right? So that means they need to be the same type of vector, so they both need to be row vectors or column vectors, and they need to have the same number of elements. And they need to be the same number of elements because when we add them, we just add the entries in the same position, right? So if we had something like u equals the vector 5, 2, and let's let v be the vector -3, 4, we can add those 2 vectors because they're the same size, right? They're both column vectors, they're both 2 by 1, and so if we did u plus v, we just add the corresponding entries, right? So that would be like 5, 2 plus -3, 4. They're the same size, and so each number has something to add to it, and so when we add those 2, it would be like this. I'm just going to do the details on this one just to be clear about it, but you can see we just add the corresponding entries, and we get a new vector, 2, 6. And we'll look at that one visually in just a second here. We'll add those 2 together again. Just to kind of be more clear about that, like if we had 2 different size vectors, like let's say we did t is 1, 2, and let's say q is the vector 7, 6, 5, we would not be able to add those 2 vectors together because they're different sizes, and they therefore don't have corresponding things to add to them, right? So if someone asks you to do t plus q, we would just say, oh, that doesn't exist because the vectors are different sizes. Just to see if this is making sense and to drive home that concept, I usually like to ask people just to give one a try. And so if S was this 5 or 1 by 5, excuse me, 5 by 1 vector, let's just make it 1, 2, 3, 4, 5. And let's let T be another 5 by 1, minus 8, minus 4, 3, 9, 0. Right, we should just be able to kind of easily write down S plus T. I would encourage you to give that a quick try, just make sure it makes sense. It's really kind of an easy one. You could probably do it as I'm doing it. We just add the corresponding entry, and we get 1 minus 8 is minus 7, 2 minus 4 is minus 2, 3 plus 3 is 6, 4 plus 9 is 13, 5 plus 0 is 5. Right, but again, we were able to do that one because they have the same size vectors. All right. Next thing we should just look at here is what happens when we multiply a vector by a constant. We'll talk about multiplying vectors and matrices and things later, but we're taking it slow here. So when we multiply a vector by a constant, every entry gets multiplied by that constant, right? Or we could say that it gets scaled by the constant, which is why we call them scalars, right? So a scalar, like, let's use the same value. So let's let this u be the same. We'll keep the same s up here, and we'll use them down here as well, right? So if I did like 2 times u, right, it would just be taking this u and multiplying both these entries by 2. So it'd just be 2 times 5, 2. Each one of those get multiplied by 2, and we get 10, 4. Right, really easy. And it could be fractions too. So something like minus 1/3 times s. Let's let this be the s, right? It'd be minus 1/3 times each one of those. 1, 2, 3, 4, 5. And each one of those just gets multiplied by minus 1/3, which just puts them over -3. So it's like minus 1/3, minus 2/3, minus 3/3, minus 4/3, minus 5/3. Right, so when you multiply a vector times a scalar, every entry in the vector gets scaled by that scalar. Okay, that's why it's called a scalar. All right, let's put the two concepts together and give this one a try. So try minus u plus 4 times v. And let's use these v and u in this problem. Right, so minus u, and again, I would recommend you pause it and give it a try, but let me just give you a hint in case you're still a little confused. Minus u is like minus 1 times u, so that'd be 5, 2. And 4 times v would be 4 times the vector v up here, so minus 3, 4. All right, so the approach here is to multiply each vector by the scalar and then add those entries together. Right? And so we'd end up with minus 5 times minus 5 minus 2 plus minus 12, 16. Add the corresponding entries to get minus 17 and 14. All right. So that's how we deal with scalar, or excuse me, vector scalar multiplication and combining algebraically. And now we're going to look at what that looks like visually on some graphs. So a lot of times I bring this stuff back to R2. And so R2, I don't think we've seen that notation before. So the script R with a 2 kind of looks like an exponent. I write it like this. You do like double line R with a 2. That means real numbers, so the R stands for real numbers. And then the 2 means it has 2 entries. And so they're things that look like x1, x2. Okay, so we're going to be thinking about R2 a lot, especially whenever we want to visualize one of these concepts. And so let's go ahead and plot the vectors that were in the last page. So I'm going to go ahead and plot u and v right here. And I suppose I should just write them down on this page too. So let's go ahead and plot u equals 5, 2. And let's plot v equals minus 3, 4. Right, so we've got our Cartesian axis. A lot of times in previous classes we call that the xy axis, but here we're calling it the x1, x2 axis, right? And so let's go ahead and give it some tick marks. 1, 2, 3, 4, 5. Try to equally space them. We can easily plot those values, right? So we're going to plot u. We go out to 5, 2. That's the point 5, 2, right? And then the vector is the arrow that points out to that point from the origin, right? So this is the vector 5, 2. And then the vector minus 3, 4, we do the similar thing, right? So minus 3, 4 takes us up here. That's the point minus 3, 4, and then the vector minus 3, 4 points out to there from the origin. So that would be the vector v. Right, so it's very easy to just plot vectors, especially if they're in R2. But what we want to look at is what happens when we actually add vectors graphically. And so like it says right here, when we add vectors graphically, you place the base of one of them at the end of the other while preserving their original direction. Okay, so I'm going to go ahead and just redraw the graph we just drew right here and then talk about adding them. So let's do the same thing. 1, 2, 3, 4, 5. I know this is a little tedious, but I strongly recommend you redraw this and have them just do what I'm doing here. Right? It's going to be helpful for you. So here's the vector u, 5, 2. And then the vector v, minus 3, 4. Okay. So if we want to actually add vectors, well, for one thing, we already know what happens when we add them because we did it on the last page, right? So when we add these two things, wherever it is, we should get 2, 6. And so we'll see what happens when we do that graphically. So like it says, we place the base of one at the end of the other while preserving their direction. So the way I like to think about that is, I took my pen out of its case here. And I think about like copying this vector. So I'm going to put the pen over the vector. It's about this long, right? So here's my vector. And then you just kind of preserve the direction. So I'm sliding it up. Move my hand out of the way. And now this piece of the pen right here is going the same direction and the same length as u, but it's at the end of v, right? And so u plus v is going to be the vector that gets us out to right at that point, right? So here is u plus v sort of graphically, right? And so that vector right there would be, or technically I took v and I added u to it. So really this vector is the vector taking v and then adding to it u, right? Because let me just do that again. I took this vector u, I copy it, and I put it over here going in the same direction, right? So that's parallel to that line. We could do the same thing with v. So here I am going to copy v. I'm going to make v the same length, same direction. I'm going to slide it over here, and you could see it ends up at the same exact spot, right? So this line right here would be u plus v. Okay? And both those points go out to right here, and you can see that's approximately at the point 2, 6, which is what we thought it would end up being. But to be clear, the actual vector u plus v, like this is how we do it. We think about copying the vectors and putting them on the ends of the other one to get to that point. But the actual vector u plus v is the one that starts at the origin and goes out to that point, right? So I'm going to do it in another color here. This is actually the vector u plus v. So this right here, let me write it out here. This is u plus v, or v plus u, same thing. Right? So the actual vector u plus v is the green one. Right? I'm just showing you different ways to sort of get to that point. Just to be really, really clear about that, I'm going to redraw it right here. So the vector u plus v goes to 2, 6. You can see right here, 2 up to 6. And so this, just to redraw it, is the vector u plus v. See I'm doing my vector signs, and we see we get to the point 2 comma 6. And notice what else would happen. Like if we took two vectors here, right, u and v, and we add them together, doesn't matter if we did v plus u or u plus v, they both end up at the same point. And when we do those two, it's like creating the fourth walls of a parallelogram. Right, so we take two vectors and then we add them together like that, it makes a fourth wall of a parallelogram, which is kind of an interesting thing. Even in higher dimensions, this is going to happen. So notice that when we add, slide this up, adding two vectors, u plus v, in R2 corresponds to the fourth vertex of the parallelogram that's formed by the vectors u, v, u plus v, and the vector 0. Right, so this fourth parallelogram, the fourth corner here is just the 0 vector because it's at the origin. Right, so the 0 vector is just 0, 0. It's like the origin. Okay. So we've kind of learned about what vectors are, how we deal with them a little bit algebraically, what they look like in some sense, especially in R2. And the next thing we're going to look at here is, visually speaking, what happens when we multiply by scalars and combine them and things. Okay, so that's what's on the next page here. And then we're going to really switch back to linear algebra and see how this stuff applies in linear algebra once we have an idea of how it all works. All right. So what happens when we multiply a vector by a constant c? And again, the other way to say constant would be scalar. So if you multiply by a constant c, you're either stretching out that vector, if it's bigger than 1, if the scalar is bigger than 1, or it's going to be shrinking the vector if the scalar is between 0 and 1. Okay, so let's mess around with the same u again. So our u from the last page was the vector 5, comma 2. I'm going to go ahead and draw that vector on both these graphs, and then we're going to scale it. So 1, 2, 3, 4, 5, 1, 2. Right, here's the vector 5, 2. That's our u. And I'm just going to draw it here as well, because we're going to need it on both. Right, so there's our vector u. If you multiply the vector by something bigger than 1, it just takes that u and it stretches it out. So let's look at 2u. So 2 times u, which we already messed around with on the first page, is multiplying both those values by 2, so it becomes 10, comma 4. And notice that if we plot that vector on the same graph, it's just going to be the exact same vector, just stretched out, right? So that's 5, so let's plot 10, 4, 5, 6, 7, 8, 9, 10. We got to go up 2 more spots. And you can see that what happens here is it's just the exact same vector, just extended. Right, so the green line now is 2u. Right, if we did 4u, it would get 4 times as big. 10u gets 10 times as big, right? So that's why it's called the scalars, because it's scaling that vector. And a similar thing happens if we multiply by a value less than 1. It gets shorter. So if we looked at 1/2 u, right, that would be 5/2 1. Right, so just to be clear, 5/2, comma 1. So let's look at what that looks like. 5/2 is 2.5, so that would be... Did I make this go out too far? 1, 2, 3, 4, 5. No, it's okay. So 2.5 would be 1, 2, 3, 4, 5. Just looks too far for some reason. Anyway, 2.5 would be right here, comma 1, and you can see it's like halfway up the line. So the green line there would be 1/2 u. Okay, so visually speaking, taking a vector, multiplying by bigger than 1 is going to stretch it out, And if you take a vector and multiply by less than 1, it's going to shrink it down. If you multiply by a negative number, which is the next thing down here, it just switches the direction of the vector. In other words, subtraction of a vector can be thought of as adding the negative. Okay, so we'll look at that in a second here. So first, let's just multiply by a number less than 1. Let's do the same vector again. Let's redraw our vector 5, 2. 1, 2, 3, 4, 5, 2. Here's my vector u again. And so if we did like -1 times u, or minus u, that just switches the numbers around, right? So it becomes -5, -2. And so it's the exact same vector, but instead of going 5 this way and then up, we go 5 the other way, and then 2 down. And so it's literally the exact same vector. It's just pointing the other direction. Right, so multiplying by -1 just took this vector and like flipped it over so it's going the other way. And if we did it by a bigger number, it would just do the same thing, but then also stretch it. So for example, -2 times u would be -10 -4, right? And if we think about where that is, it's going to be 10 this way, 4 down. It's just going to be the same vector, just stretched twice as far in the other direction. So that would be -2u. Right, -3u would go 3 times as far the other direction, etc. All right. So let's subtract something and just see what that looks like. Let's again work with the same vectors. We're going to work with u and v some more. And so I guess before we get too far, I'm just going to go ahead and draw u and v again down here. And then what we'll do here is we'll draw the subtraction of the two. And so let's just remind ourselves that we're messing around with u equals 5, 2, and then v is -3, 4. So let's draw those on here again. So u is 5, 2. V is -3, 4. Okay. So over on this graph, what we're eventually going to do is we're going to do subtraction. We're going to do u minus v over here. Okay. And so before we actually go ahead and do that, let's just combine them together on this graph, and then we'll redraw what it actually looks like over here. Okay. So v is this, right? Then minus v is going to be this exact thing, but it's flipped over this way, right? Because we just learned on this thing that if you multiply by -1, it just takes a vector and flips it around the other way. So if we took v and we flipped it around, minus v would just be the same thing going the other way. And so that's the first thing I'm going to draw here is minus v is going to be multiplying these by -1, so it'd be 3, -4. And so we'll go over here. 1, 2, 3, -4. You can see it's the same vector, just pointed the other way. Okay? So if we wanted to do u minus v, we could think of u minus v, which again, we're going to draw it over here in a second. We're just working out the details here. If we thought about u minus v, that's the same thing as doing u plus minus v. Right? You can add the negative. That's like the same thing. And so in that light, we could do the thing we just did in the last page, which is if we want to add minus v to u, we copy minus v and we add it to the end of u. Right, so I'm going to take v. Here I am copying v. I'm just going to copy it. It's that length, that direction. Get this bug out of here. There's minus v. And then we're going to slide it over to the u, and this is going to be u minus v. Get that over here again. Right, so I just copied minus v and I added it to the end of u. And so this green line is going to be u plus minus v, or u minus v. Okay, so to this point. Did I do that right? And it's not perfect, but you'll see what it's okay. So that point would be u plus minus v, and then the vector would be the vector that points out to that value. Right? And so if we actually did the algebra, which we can do right here, u minus v is going to be 5, 2 plus 3 minus 4, which is going to be 8 minus 2. And that's approximately where that is. I didn't do the best job of copying things over. I think that line's not quite straight, and maybe it's a little too long. But anyway, that's the general idea, is the point 8 minus 2, which is approximately where that point is right there, is the point u minus v. And so if we wanted to draw it over here, we go out to 8 minus 2, and then draw the vector out to that point. That would be the value u minus v. Just showing you visually what happens there, and then backing it up with the algebra that we already learned about on the previous pages. Right, let me just review that real quick in case I know that's looking confused. So we had v and u. Right? We wanted to think about u minus v. So the first thing we did is we thought about minus v. So minus v is flipping v around to the other side. And then if we copy that minus v and add it to the end of u, it takes us to 8 minus 2. And so we can see that u minus v ends up being 8 minus 2. Graphically, this is the graphical version, and then here's the algebraic version kind of backing up that answer. Okay. So all of this can be extended to higher dimensions. So everything we've done so far on these pages, this is all in R2, right? It's two-dimensional. It's easy to draw in R2. We know how to do that. We can extend all this stuff to vectors in higher dimensions. So just the first thing we'll look at quick is just vectors in R3. So as a quick reminder, this R3 means real numbers with 3 entries. And so those look like x1, x2, x3. Right? That's what R3 looks like. And it's possible to plot those by hand. Definitely possible to use a computer to do it, right? So we can plot these vectors in 3 dimensions. It's definitely difficult to do by hand, especially if you're artistically challenged like I am, but it is possible, right? So for example, we could think about the point 4, 1, 3, and we could plot that by hand. If you're in like a Calc 3 class or a multivariable calculus, you might think about that as an x, y, z value. But here we're thinking about it as x1, x2, x3, right? And so it's challenging to draw something in 3D, but it is possible, right? So you have like an x1, x2 Cartesian axis, and then you add like a third one, which oftentimes goes out to the side like this. That might be the x3. Really, it should be coming out of the page, right? So if x1, x2 is that, x3 should be my pen right now, and it should be coming out of the page. And so the way you kind of represent that on a 2D flat piece of paper is by kind of drawing your other one out there. And so we can go out 4 in the x1 direction, 1, 2, 3, 4. We could go out 1 in the x2 direction, 1, and then we would go out 3 in the x3 direction. And so 4, 1, 3 might be something like this point right here. But again, it's really hard to do by hand. I usually try to avoid drawing things in 3D by hand, which is usually why I stick to 2-dimensional examples. But just to be clear, like you can technically draw things in 3 dimensions by hand. And all this material extends beyond 3 dimensions, so vectors in Rn. This is a general way to write, we don't know how big the vector is, but it has n entries, right? So Rn means vectors with n entries, so some arbitrary number of entries. And you can see the n refers to the number of vectors, entries in the vectors. So for example, we've seen R2 so far. Those look like x1, x2, right? We just looked at things in R3 above here. R3 looks like x1, x2, x3. But we can have any number of entries, right? So we could have things in like R5. Right? R5 would have 5 entries, right, etc. Right? We could have as many entries as we want. R10, R a million. And to be perfectly honest, in real applications, we often have really, really big vectors. But the thing I'd like to sort of point out or have you think about is, can we visualize vectors? How many can we visualize? Well, we've drawn things in R2, right? These are R2 vectors that we've been drawing on the last page. This is sort of an example of something in R3, but we can't draw something in R4. And so we're only really able to visualize things up to R3. And so when I draw visual examples, as I've mentioned a bunch of times, I'm going to use R2. Occasionally, maybe I'll show you pictures in R3, especially if I can print them out from a computer or something. We cannot think about visualizing things in R4, but all the stuff we're talking about does extend to those dimensions. We've already actually covered this too, but here it is just written one more time. The 0 vector, which can be written as the number 0 with a vector sign over it, or a bold-faced 0. It's just a column of all zeros. And so it depends on what space we're in, right? So in R2, the 0 vector is just 0, 0, because there's only 2 entries in R2. But if we're in R4, right, we write literally the same thing, just 0 with a vector, but if we're in R4, all of a sudden that means that there's 4 zeros. Okay, so just be aware that the 0 vector, how many zeros there are, just depends on what dimension we're in, and you could just think about these as the origin, right? It's right at the origin, right at the middle of the graph. Right? In other words, if we're kind of thinking about this concept right here, this point right there, right at the origin, would be 0, 0, 0. Right? That's the 0 vector in R3. Okay. The properties at the bottom of the page are things that apply to most numbers, right? So, first of all, notice that in the below thing here, U, V, and W are all bold in all these, and so that means they're vectors, right? So they're in Rn. Right, so just to be clear, those are vectors. And then the C and the D are just written as non-bolded, italicized things, and so that means they're scalars. And so what this is just saying is, like, you can change the order in which you add vectors, right? You can change the way you associate grouping them before you add them, right? Adding 0 to a vector keeps it the same, right? When you add the negative version of a vector, you get sent to the 0 vector. So you can distribute scalars through vectors, right? So a lot of these things make sense, and they're probably things you would have assumed if I didn't write this down here. The thing I'd like to point out, though, is everything in here, or most of the things in here, are addition and subtraction, right? There's a couple multiplication things here, but notice how there's nothing here that says you can change the order in which you multiply vectors. And so multiplying vectors and matrices as well is actually much more complicated and has more rules and more sort of strange things that happen than with numbers. So I just want to make that clear. We haven't gotten there yet, and we'll see this in more detail. But notice that, like, if you multiply 4 times 5, it's the same thing you get as 5 times 4, right? In both cases, you would get the number 20. But if we're talking about vectors, for one thing, oftentimes you can't multiply 2 vectors together, and moreover, you definitely can't change the order in which you multiply them. Okay, so we'll see more on this later, but that's the thing that I just wanted to point out that's kind of missing from these properties, is you can't change the order of multiplying vectors. Multiplying vectors is much, much different and more, I guess, more complicated, if you will, than multiplying numbers. Okay, we'll see that in some subsequent sections here, but that's just what I want to point out so far. Okay, wonderful. So those first 4 pages, I know we spent about a half hour looking at those first 4 pages, but they're mostly just like definitions. How do we add vectors? What is a vector? What do they look like? Things like that. You know, the following 3 pages are really how we start to apply these concepts in linear algebra. So, not to scare you or anything, but the first 3 pages or 4 pages that we just did shouldn't be a big deal. The last 3 pages are really what we want to focus in on. I'm just trying to say that now because I feel like sometimes people get fatigued after they see those first pages and they just sort of tune out, or they don't absorb the next couple pages, but the next couple are actually what's really important. Okay? So we've been building up to this concept of what a linear combination is, right? So that's really what we want to talk about or start talking about, but we needed to know what vectors were before we did that. So when you multiply vectors by scalars, as a quick reminder, scalar just means constant numbers. When you multiply vectors by constants and then add or subtract them, you're producing linear combinations of those vectors, right? That's a word that's going to come with us the rest of the course, linear combination. So formally, if we've got a bunch of vectors, v1 through vp, right, and I know they're vectors here because they're bold, and we've got a set of scalars, c1 through cp, and I know they're scalars because they're not bold, then the vector y, defined as this sum, is a linear combination of the vectors with weights c1 through cp. Okay, so look at what's going on in this expression. We're taking each vector, we're multiplying it by a scalar, and then we're adding all those products together. Okay, and the c's could be any weight, and so maybe 0, right? So if you multiply a vector by 0, it just kind of goes away. And so this is what's called a linear combination of v1 through vp. Right? So linear combination of v1 through vp with weights c1 through cp. So just as a quick example, just to get our feet wet here, let's let v1 be, or v minus 1, 1. Oh yes, v1 I mean. Let's let v2 be 2, 1. And let's let v3 be minus 4, 6, right? So we're taking some vectors in R2. Let's do a linear combination of those vectors. So let's do minus 3v1 plus 2v2 minus 1/2 v3. Right, we'll write out the algebra for that, but what I'd like to just point out here is that we're doing a linear combination of the vectors. Using the vocab here, this is a linear combination of vectors v1, v2, and v3 using the weights minus 3, 2, minus 1/2. So just using some vocab, writing down what we're looking at here. And of course, we can do that multiplication, right? We know that when we multiply vectors times scalars, it just scales the individual entries, and then when we add or subtract them, we just combine the entries in the same location, right? So in other words, minus 3v1 is really this, 2v2 would be this, 1/2 v3, oops, don't want to write v3, I want to write what the vector is. V3 would be minus 4, 6. Right, so scaling each one of those vectors just means multiplying the entries by that number. And so this becomes 3 minus 3 plus 4, 2. And then in this case, you divide by minus 1/2, so we'll have 2 minus 3. And then when we add them together, we just add the individual entries. Right, so 3 plus 4 plus 2 is 9. Minus 3 plus 2 minus 3 is minus 4. Right, so this 9 minus 4 is a linear combination of vectors v1, v2, v3. Okay, so that's, again, this is sort of defining what a linear combination is, showing you a quick example of one algebraically. Now let's look at what a linear combination actually looks like visually, right? So visual representation of linear combinations. This is a really great picture. This picture comes back quite a bit. I often put this picture on test 1 actually and ask questions about it, so this is a good picture to kind of be familiar with. So let's look at what's going on here. So first, what's happening is we're plotting two vectors, v1 and v2. Right, the same vectors as above there. So v1 is minus 1, 1, and you can see here it is. So here is the, the x2, x1 axis. So we've got the x2 axis going through the middle. We've got the x1 going this way, right? Here's the origin right in the middle. And so v1 is the point minus 1, 1. So left 1, up 1. That's right here. Right? I'm drawing it in green. You can see this is the v1 vector. The v2 vector, 2, 1, is right here. So you go 2 to the right, 1 up. This one would be v2. Okay. Now, what's being shown everywhere else, all these other points, where it kind of looks like a lattice, the lattice that I'm highlighting right here, or this piece of the lattice that's kind of in bold, this is scaling v2, right? So if this is v2 right here, then 2v2 would be stretching that out twice as far. 3v2 would be stretching it out 3 times as far, right? 4v2 would be going even farther. And then going the other way is multiplying by negatives. So if we multiply by negative 1, this v2 flips around and goes the other way. If we multiply by negative 2, it flips around and goes twice as far the other way, right? So that's kind of what we had seen on the previous page. And we see the similar kind of thing with v1, right? So if this is v1 right here, 2v1 is stretching it out twice as far, 3v1 3 times as far, right? This point right here is 4v1 because it's going 4 times as far. And the same thing happens going the other way. Minus v1 is flipping it around, minus 2v1 flipping around twice as far, etc., etc. Okay, so the x going through the middle of this line and this line are just the scalar values multiplying v1 and v2. What this is also showing us is how we can get anywhere on this plane, anywhere you put your finger down or your pen or whatever, you can get to by some linear combination of v1 and v2. So this point right here, for example, right, it's saying it's minus 2v1 plus v2. So minus 2v1 would be going this way twice, right? So there's minus 2v1, you can see it right there. And then if we add v2, it'd be like we copy and pasted v2 and added it to that point. So let me do that. Here, I'm copying v2. Here's my pen again. I'm copying v2. I'm adding it over here. Oops, look, so it took us right to that spot. So that point right there is minus 2v1 plus v2. Right? If we wanted to think about this point right here, we want to go 1.5 steps in the v1 direction and then 1 step in the v2 direction. So 1.5 v1s would be 1.5. Right? So this point right here where my pen is would be 3/2 v1. And then when we add v2, we move this direction, and that would take us right over to here. Okay? And so, again, very important kind of picture. I'd put this on tests and things like that. And just to be clear about what it's showing linear combinations of v1 and v2. Right? We've looked at a couple so far. And notice how those linear combinations cover the entire R2 plane. Okay, so if we have two distinct vectors like v1 and v2, we can get anywhere in the R2 plane by taking some linear combination. To kind of drive that home a little bit, notice there's some letters in here, right? So there's u. Let's figure out how to get to u. So we're going to write down how we get to u. U equals some linear combination. There's also w, right? So w is right here. Yeah, I'll do that in blue. W is right there. We'll think about how do we get to w. Are those the only two ones on there? Those are the only two ones on there on this particular one. So let's start with u. Right, so here's u. How do I get to that point by using combinations of v1, v2? Well, if I want to get up here, I want to go this direction, right? So I can go 3 directions of v1. And then I want to go this way 2 steps. And this way 2 steps would be going v2 in the negative direction, right? So this u right here is 3 steps in the v1 direction, and then 2 steps in the minus v2 direction, right? So let me do that again. 3v1 would be 1, 2, 3. You can see it's labeled right there, right? And then if we go 2 steps in the minus v2 direction, well, minus v2 is going this way. So here I am at v1. I'm going to go 1 step in that direction, 2 steps in that direction. So to get to u, I go 3v1 minus 2v2. Take a second to think about how would we get to w. Right? I would need to go this way and then half a step that way. All right, so w is going to be 2.5 steps of v1. Right, so here's 1 step of v1, 2 steps of v1. I want to go halfway because it's in line with that. And then I want to go this way half a step. And so that way half a step is going to be halfway to v2, right? So this way half a step would be minus 1/2 v2. Okay, we're going to come back to this picture after we learn something on the last page, but the thing you should realize so far is no matter where I put my finger down on this page, or pen or whatever, some linear combination of v1 and v2 can get you to that point. And it's a little bit of a good exercise just to try that a little bit. See if you can get places, right? Just put your finger down. How do I get right there? Right? See if you can get right there. Okay, we'll come back to this picture in just a minute here after we learn the definition of spanning sets. Okay? And then we'll put it all together on the final page here. Okay. So, the set of all linear combinations of a bunch of vectors, so we have a bunch of vectors v1 to v2, the set of every single linear combination you could ever think of is called the span of that set. Okay, and here's how we denote that. Span, and then we write the vectors down inside curly braces. Okay, so in other words, that is, span of v1 through vp is the collection of all vectors that can be written in the form this. Right, so here I am doing a linear combination of those vectors, where c's are some scalar. Okay, so switching back to the last page, this image is a visual representation of the span of v1 and v2. Right, it's showing all the different possible linear combinations of v1 and v2. So this picture right here, and you should add this title to it, it's a visual representation of the span of v1, v2. Okay, because we're showing all of these different linear combinations of those two vectors in this particular picture. It's a very important concept, the span. And oftentimes we think, is this vector in the span, right? And so let's think about that. So if a vector, let's say b, let's say if we want to know the vector b is in the span, so vector b is in the span of a bunch of other vectors if it can be written as a linear combination of those vectors. For some scalars C1 to CP. Okay, so let me say that again. A vector is in the span of other vectors if it can be written as a linear combination of those vectors. Right? So for example, back to the last page again. This is two examples, right? This is kind of the thing we just wrote down. U equals 3v1 minus 2v2. So this is sort of indicating that, another way to say that is U is in the span of those vectors. Right? Because it can be written as a linear combination of those, right? We could say the same thing about W. W is in the span of v1, v2 because it can be written as a linear combination of them. Okay? So if we want to know if a vector is in the span, we want to think about, can I write that vector as a linear combination of the other vectors? All right. Let's look at some graphical interpretations of this span. So let's look at a single vector. So you can see we're going to look at the span of a single vector, we'll look at the span of a couple vectors, and we'll keep going, right? So let's look at the span of a single vector. So here's my vector v1. I don't know what it is. It's some vector in R2. Well, let's multiply that thing by 2. Right, so just to be clear, I should maybe write that down here. If we wanted to do the span of this vector, it's going to be some constant times that vector, where C1 is any scalar. Right, so the span of a single vector just means multiply that vector by a constant. Well, if this is v1, 2 times v1, we just learned on the last page, sends that thing twice as far, right? That would be 2v1. 3v1 would send it 3 times as far. Right? That would be 3v1. Right? 4v1 would be 4 times as far, etc. Okay, so multiplying by positive numbers bigger than 1, send it out this way. If we multiply by negative numbers, we learned that it flips it around, right? So this would be minus v1. Minus 2v1 sends it twice as far the other way. Right? We could do minus 2.5 v1. It would be 2.5 times v1 going the other way. Right? So if we take a vector v1 and we do the span of that, it just creates a single line, right? It just extends that vector in both directions. And so the span of that vector is the entire line. So let me just draw that down right here. Span of v1 would be this entire line. Everything on that line would be the span of v1. Okay, and you can do that. You can do the same thing in higher dimensions as well. So here's my attempt at doing it in R3. Right. So if this is, how about this is v? If this is v1, then 2v1 sends it this way. 3v1 sends it this way as well, etc. Right? Minus would send it the other way. Etc. And so the span, again, is going to be the entire line. And so notice that whether we're in R2, this is in R2, or we're in R3, it doesn't matter. The span of a single vector creates a line. It just extends the vector in both directions and creates a line. Okay? So what happens if we go into 2 vectors? So the span of 2 vectors, like we saw on the last page, right, given 2 vectors v1 and v2, like we saw on the last page, the span creates a plane. Right? So this is exactly what we saw on the last page. And this is the same graph as the last page, right? This is showing us that if we have v1 and v2, okay, then the span of v1, v2 is the entire plane. And it would be the same thing in 3 dimensions, right? So this is what it looks like in 2 dimensions. Let's pretend we're in 3 dimensions now. So I know it's kind of hard to see here, but there's actually 2 vectors on this. There's vectors b, there's a b right here, and then there's a vector a right here, right? And so a and b are both in R3. You can see that they're 3-dimensionals. But the span of those 2 vectors is the blue plane, right? So we had 2 vectors that are in R3. When we do the span of them, it creates a plane and actually extends out in all directions. It's just kind of showing a piece of that plane. And so no matter what dimension we're in, when we do the span of 2 vectors, we get a 2D plane, right? That's really key here. I'm going to write that right here. The span of any 2 vectors, no matter what space we're in, will end up being a 2-dimensional plane. In R2, it fills up the entire R2 plane. in R3, it creates like, this is kind of like a piece of paper angled through a room, all right? A piece of paper is two-dimensional, but if it's in a room, the room is three-dimensional, okay? So the span of one vector creates a line, whether in R2, R3, R4, whatever. The span of two vectors creates like a piece of paper you could think about, whether it's in R2 or R3. If we create the span of three vectors, it creates a 3D object, right? So it would be kind of like this. It would be like, let me just draw a quick sketch here. This is x2, x1 plane, right? And so if we had R3 would be the third axis would be my pen coming out of the page, right? And so we draw that kind of like this we saw before. And so if we did the span of three vectors, it would not just create a two-dimensional plane, it would create a 3D cube because this axis is coming out of the page. All right, so if we had like, well, let me just do it like this. If we did the span of any three distinct vectors, we would get like a cube. Right, that kind of goes out in all directions. So it creates a three-dimensional object. Like a cube. Okay. Really key concept there. I know that can be tricky, especially if you haven't seen this stuff before. So please do let me know during any of our sessions if you want me to clarify any of that. I can go over things in general or more specifically, and help with my document camera potentially. Notice that I kind of wrote over here, but you can't actually visualize the span of four or more vectors because we're getting into dimensions that are too high for us to really think about carefully, right? And so let me just review one more time. If we have the span of a single vector, no matter the dimension of the space we're in, whether it's in R1 or R2 or R3, when you do the span of a single vector, it creates a line. The span of any two vectors, whether we're in R2, R3, etc., creates a two-dimensional plane. The span of three vectors creates a 3D object, okay? It's true that the span of four vectors creates a four-dimensional object. We just don't know what that looks like, and so we can't actually draw something like that. All right, so we're really getting into some of the linear algebra here. This is great. We're just going to finish off with a very typical kind of question that both has lots of applications, but also just shows up a lot in notes and homework and tests and things like that. So so notice how it says in the previous figure, image 8. So image 8 is just the lattice picture, right? This is, you can see figure 8, it says right here. So in this picture, it says, taking linear combinations of v1, v2 produces infinitely many other vectors. All right, and so what that's saying is, what I said a bunch of times is, no matter where I put my finger down on this page, I can get to it with some linear combination of v1, v2, okay? So it creates infinitely many, the span of two vectors creates infinitely many other vectors. So figure 8, as we already wrote down, is a visual representation of the span of two vectors. A very important question we often ask in linear algebra is, given some vector, is that vector in the span? Okay? And so in a picture like this, if we wanted to know if U is in the span of v1, v2, we want to see, can I find some linear combination that puts us to that spot? And in R2, if you're doing the span of two vectors, anywhere is in the span, right? But if we're looking at that three-dimensional example, asking, so this is, as a reminder, this blue square is the span of two vectors A and B. And so if we want to know if a vector is in the span of A, B, we would want to know, is the vector in that blue square somewhere, right? So if it's over here, maybe it's not in the span, but if it is, it would lie on that piece of paper. Okay, so algebraically, here's how we're thinking about that. So we have two vectors, v1, v2. This is kind of like, you could think about this as like the A and B from the last picture I just showed you. We can see that these vectors are in R3 because they have 3 dimensions. Right, this one is 2. And the question is this vector B in the span of the other two, v1, v2. So just to be clear, this is two vectors, and so we just learned on the last page, this creates a 2D plane in 3D space. It's just like that picture. Right? You can think about this picture as being exactly what we're thinking about. And so if we want to know, and let's even pretend that this is our A and our B. So if we want to know if this B is in the span of the other two, like I said a second ago, the question is that vector on that piece of paper somewhere? Well, algebraically, the way we think about that, I'll write down the solution. We want to think about, are there scalars that we can multiply these two things by such that we add them together and get B? Right? So are there scalars, C1 and C2, such that C1v1 plus C2v2 equals this vector B? Right? That's the question we're trying to ask right now. And so this is an equation we can write down. It'll turn into a linear system. We can put that into a vector, or a matrix, and see whether or not there's a solution. Right? That's sort of the goal here. So let's start writing down this expression. So this turns into, when we use these vectors, the following. C1 v1 plus C2 v2 equals B. Right? We're trying to see, is that possible? Just to have some vocab here, this is what's called a vector equation. And we've seen a couple of them so far in this class. It's a vector equation because it's an equation, it has an equal sign, and it's got vectors on either side of the equal sign, right? Okay, so let's start collapsing this down and create a linear system. So we know that we can multiply the C1 and the C2 into those two vectors, right? That's what we've learned in this section so far. And then once we do that, that's a linear system. Let's write down the linear system, right? So this says like C1 plus 3C2 equals -1. That's the first equation. Right? The second equation says minus C1 plus 2C2 equals -4. The third equation, or the third row here, says 0C1, so I'm just not going to write that. It just says -4C2 equals 4. I'm going to put these curly braces around it to show that it's a linear system. In other words, the C1 and C2 that satisfy the first equation also have to satisfy the second and third. And this is now something we know how to solve. This is something we've learned how to solve in the last couple sections, right? This is a system of linear equations. And we know how to solve that. We know how to put it into a matrix, an augmented matrix to be more specific, and solve using via row reduction. Right. So that's how we can figure out if B is in the span. Right. We're trying to just to remind us what we're trying to do. We're trying to figure out if B is in the span of the other two vectors, and we've just realized, hey, this can be a linear system that we can put into a matrix and solve. So let's do that. And we're going to need some space here, so let's leave some space. So let's put this linear system into a matrix. Okay, so we've got our pivot in the upper left-hand corner as the number 1. That's great. That's a good start. We want it to have zeros below it, and that is a 0, so that's good. But we want to use that one to cancel out that one. And so we are going to just do row 2 plus row 1. Because that will get the 0 in the second spot like we wanted. The first row stays the same. Second row becomes this. Okay, so that's good. Because we've got a pivot right here, and it's got zeros below it. That's exactly what we wanted. Now we want to have a pivot down to the right, so we want this middle 5 to be a pivot. And so let's divide this row by 5 to make that a 1. and then we'll use that 1 to cancel out the 3 and the minus 4. Right, so you can do these steps kind of multiple times when you start to get the hang of it. I'm going to try to go a little bit slow here to just make it a little easier. I think I'm going to go ahead and multiply row 3, divide row 3 by 4 as well, just to put a 1 in that spot. That'll also be helpful. So the first row stays the same. Second row gets divided by 5. Third row gets divided by 4. Oops, I forgot to change that to a 1. That should be a 1. Okay, and that's good because we've got a pivot in the first spot. Now we've got the pivot in the second spot, which is what we wanted. We want to use that 1 to cancel the 3 and the minus 1. I'm going to do that in one step. So I'm going to take row 1 and I'm going to subtract 3 row 2. And I'm going to take row 3 and just add to it row 2, because that will cancel out the 2 non-pivots in the second column. And it gives us what we wanted, because the bottom row becomes a bunch of zeros. And so now this is fully reduced. This is RREF. Right, because we've got a pivot. It's the only non-zero in that column. Down right, pivot. It's the only non-zero in that column. And then we've got a row of zeros down at the bottom. That's exactly what we wanted. And this just tells us the number. The solution, I mean. Right, just so as a quick reminder, this is like the C1 column. This is the C2 column. This is the equal sign. This is the constant. So when we write down what this system actually tells us, the system tells us that C1 is 2 from the first row, and C2 is negative 1. So we have a solution. Right? So if I plug C1 equals 2, C2 equals negative 1 into these equations, I should get B. In other words, a linear combination of V1 and V2 actually does equal B. Right? So just to be very clear, what we just found out is that we were trying to figure out this equation. Does some linear combination of V1, V2 equal B? And what we just found is that yes, in fact, 2 times V1 plus minus 1 times V2 does in fact equal the B that we were hoping for. Right, so we just, in other words, we saw 2V1 plus minus V2 equals B. And so yes, we found a linear combination of V1 and V2 that equals B. Okay? And so just to kind of write down the final answer here, if this is a test question or something, we would say, okay, we just found that the B value, which is minus 1, minus 4, 4, is a linear combination of V1 and V2. And it has weights. The weights are the C's, right? So the weights would be 2 minus 1. In other words, B, since B is a linear combination of those two things, B, which I'll just write down this vector one more time, it is in the span of the other two vectors. And so kind of going back to our picture one more time, if we're thinking about V1 and V2 as A and B in this picture, and then the span would be that the blue piece of paper, which again expands in all directions. It goes out in both directions. The idea is that the B we just found is on that piece of paper. It's not above or below it or somewhere else in R3. It's actually on that piece of paper. So what would happen if it was not in the span is the question. Well, if it was not in the span, when we tried to solve this system, so we did this thing trying to figure out if it's in the span, and we ended up with this linear system. We put it in a matrix and tried to solve it. So if it was not in the span, what would happen is this matrix would end up being inconsistent. So it's important to write that down just because sometimes things won't be in the span and we want to be able to identify it. So if we had an inconsistent matrix in row echelon form, then we would be able to conclude B is not in the span. So that's what we would be looking for, or that's what would happen if we had the case where it's not in the span. Just to kind of reiterate again, like this material of linear combinations and span carries through the entire course, and we build on this quite a bit. And so please do let me know if there's anything here that's confusing at all.